I'm happy to introduce Group 5, who's going to tell us about Syzygies of powers and binomial edge ideals.
Okay, hi everybody. Don't know how we're supposed to follow that, but we are Group 5. We looked at the Syzygies of powers and binomial edge ideals. It says on the slide. I'm Zoe, this is Alicia, Bryan, and Abbas. So in order to motivate this problem, we need to define some things. So our first definition is a graded free resolution, which is just an exact sequence that looks basically like this. And importantly, the differentials are all degree preserving maps. And we define the ith syzygy module to be the kernel of the ith differential. Similarly, the ith graded Betty number beta ij is the number of basis elements of degree j in the ith free module in the free resolution. And then formally we get this sum, where this r join negative j is just precisely the number of basis elements of that degree. So here's an example of a free resolution. Join your favorite variables to your favorite field k. And the resolution of r mod the ideal generated by those three variables times r is just this resolution with this differential. And this is actually an example of a Kazul complex, which we'll come back later, and we'll talk about more in the later slide. So finally, we have the initial ideal. So for any term order, binomial term order, we just denote by Lm the leading binomial with respect to that term order. And then we define the initial ideal of some ideal I to be the leading binomials of the elements of that ideal. And it's a known fact that when G is closed, the initial ideal with respect to the Lex order is quadratic. And here we will denote the binomial edge ideal as JG, and we will say that its generators are just called Fij, where Ij is an edge of G, and then we have an analogous thing of the initial ideal. So the motivation for this project, which we can now state, was posed in this paper by N.A. Ronaldo and Bryan, posted in 2021, and I think published in 2022, which states that for a closed graph G, the graded Betty numbers of the powers of the initial ideal and powers of the binomial edge ideal itself are the same for all m greater than or equal to 1. And this is actually known for m equals 1. It's a theorem due to Pava. And as you can see, so these are Betty tables. The entries in the Betty tables are Betty numbers. And they are the same for the initial ideal and the binomial edge ideal. So that's nice.
Okay, so, well, as you can see in the motivation, we have powers of binomial edge ideals and initial ideas of binomial edge ideals. So it would make sense to have a tool that kind of connects all these powers. So that's the research bar, right? This is the research bar is this construction that we have over here. And yeah, we have the powers that we refer, right? Also, we have the race map, which we've talked about that before, but this could also be seen as a presentation of the research. The map is taking elements from R to R and the Tij's to Fij. That's the elements that we've talked in the construction of the binomial edge ideal in a variable T. Our objects are bi-graded. So here, as an example, we have that the Tij's have degree 1, 2, and the elements R have degree 0 and the degree of the element itself. So, important thing, the kernel of this map, that's basically our main object in here, or in the background. So the elements in the kernel are actually, are the relations of the Riesz algebra. These word relations will keep appearing many times. But the thing is that we will denote it by L, right? So keep that in mind. Now we have this theorem that comes from a mole selling a list. It was published in 2024. And basically this theorem, what it says is that our relations are generated by 3 kinds of relations. First, we have causal relations. These are constructed from 2 cliques. And well, this is how the relation looks. The cliques must be different. And then we have the Norton relations, and those are constructed with respect to an induced triangle or a C-tree, right? In this case, we introduce this notation. This is something that we did. And the notation where it's telling you is, okay, you're taking the relation, the Norton relation with respect to a clique that has vertices I, j, and k, and where you're taking the variable x or the variable y. So that's what the Egan-Markov relations are. Oh, and these that are underlined are the leading monomials. Now, the Plugger relations are relations on complete graphs in 4 vertices, or K4 induced in the graph, and this is how the relation looks like. But the theorem also says a little bit more. The theorem also talks about how these relations behave, but now taking the real algebra of the initial idea. These are analogous constructions. We won't get deep into those, but the only thing that I will add about this theorem is that the theorem does not tell us something about this set of relations being a minimal generating set, right? It's just a generating set, but not necessarily minimal. So an example of these relations. We have this graph, right? Well, we have 3 clicks, 0, 1, 2 is our first click, 2, 3 is our second click, and 3, 4, 5 is our third, right? So for example, in here, we're taking the H01 in the first click, and then the H23 in the second click, and we generate the first causal relation, but we can also construct something with something in the first, an edge in the first click, and an edge in the third click. Something like that, right? So these are just 2 examples of causal. Of course, we have more. And about Egan-Markov, well, again, we have Egan-Markov relations for induced triangles. So it's either this one or this one, right? So in these examples, we consider the first click. And the difference is that in here we're taking the y variable, and in here we're taking the x variable. Last of it is that this does not have K4 induced, right? So that means that we don't have Plugger relations. In a similar way, you can check that these are some of the relations for the other type of Rees algebra, right? The one that is about initial ideals.
Okay, so now that we know what is the relation of the Rees algebra are, we want to relate it to the Syzygies, okay? So remember that we're using L to denote the relations of the Rees algebra, that is the kernel of the map, and we will define 2 sets. The first one is the elements in the kernel, the relation of the Rees algebra that has degree m and something else. We don't care about the second entry of the degree. And the second set is the relations of the Rees algebra that has degree m and 2m. Why we have 2 here? Well, because the generators of the binomial edge ideal has degree 2. So that's why we are taking, we are taking the 2 here. The first set is an R model. And we prove that that is an R model. And the second set is not an R model, it's just a vector space. So we construct an R model from this set, from this vector space to, well, we take the elements here and generate an R model. That's this RL and this. And we have this R model, and so we have now this theorem. So this theorem says that for a binomial edge ideal, we have this isomorphism, that the first Syzygies of JG to the M is isomorphic to N, okay? But if we take a graph with no K, the R model N is just this R model. Why? Well, because if we don't have K4 induced, we don't have Plugger relations, right? And this set is just a set of Plugger relations. So that set will be empty, and and this will be, we will have nothing here, and we just will have this R model. So on our document, we have a more generalized version of this theorem, but for the purpose of this talk, we just need to focus on this binomial edge ideal. Okay, so we have that isomorphism, and we need that theorem to prove this Betty number formulas. So for a graph with no K for induced, we have that E is the number of edges, T is the number of triangles, and we have these formulas for the linear strand. What is the linear strand? It's the first row that doesn't have empty entries. So we have these formulas for JG squared. Okay, so well, let's see how this look with an example. So remember our favorite example. This example has 7 edges and 2 triangles. So we just replace the numbers and the formulas, and then we have that this is 28, this is 28, and this is 6. And the complete Betty table looks like this. Okay, so we have this for JG squared, but we to extend these formulas to JG to the M. So to do that, we need to explain the Kazoo complex, and that will be so easy.
Yeah, so as Alicia said, our main result generalizes those formulas. So for a K4 free closed graph, we have that not only are the Betty numbers the same in these coefficients for JG to the M and the initial ideal of JG to the M, we also have that they are explicitly equal to this combinatorial formula. And just to give kind of a proof sketch, so we have E, which is the ideal generated by Egon-Northcott relations, and then we have E prime, which is the ideal generated by Egon-Northcott type relations. And we showed that for both E and E prime, their minimal free resolution is a Kazoo complex, and the resolution is in fact the same. And the Kazoo complex looks something like this. And the way we showed this was by showing the leading monomials of the generators of E and E prime were coprime, which essentially means that they form a regular sequence, and then it's a well-known result that if you have a sequence of elements that are a regular sequence, they are minimally resolved by a Kazoo complex. So if anybody remembers what happens, I guess like 10 minutes ago now, that example of a free resolution with K join XYZ, in that scenario, XYZ forms a free resolution, forms a regular sequence.
So here's the same Kazoo complex with the graded structure here. So now we have these little bi-graded twists where we shift over by negative I and negative 3i. And yeah, we just have, this is now a graded minimal free resolution for this ideal here, generated by the relations. So the first thing we're going to do here is we're going to restrict by f degrees. So we're going to take the homogeneous components where where we have m and t and degree greater than or equal to 2m in x and y. So now we're going to augment this complex to the right by JGM. But we don't have this complex is no longer exact, because over here the kernel is the presentation ideal, the appropriate homogeneous components of the presentation ideal, and the image is the same homogeneous components of the smaller ideal E. However, this doesn't really matter because we have equality of the equality of vector spaces of these two homogeneous components, LM 2m plus 1 and EM 2m plus 1. And for this reason, we can take the linear strand of LM dash from the resolution of E. So now we want to think about what the Betty numbers here are. So first we see that each of these S with the little twists are actually free graded R modules of this form are negative d to this exponent. And this exponent here, it tells us how many leading monomials in the Tij there are of a certain degree. So now just multiplying the exponent we get here with the exponent of the S in the corresponding place in the free resolution, you get this formula for the Betty numbers of LM dash. And then by the isomorphism, we've proven this equality also holds for the Benny numbers. And it turns out this procedure is a bit more general, and we can apply this to the initial ideal as well. And we obtain the same formula here. And so thank you. That's
Great. Do we have questions for our speakers? Oh, please.
What was S defined as?
S is the polynomial ring R, adjoined with all the variables T, I, J, which map to def I, J, T.
And so it seems like in all of your resolutions, you have like exactly 2 copies of S, right? Because you have like two coordinates for your twist, right?
Oh, those are the bi degrees. So
Okay.
S inherits the kind of it inherits the kind of bi degrees from the Riese algebra just by like where the components are mapped to. So like the Tijs would be mapped to things of degree 1 and 2 in the Riese algebra, so they have degree 1 and 2.
Do you mind going back to the slide? Where you
Yes,
have this
of course.
definition? That might help.
Oh, okay.
Oh, sorry. Where was that? Yeah, so great. This degree 1 and T, degree 2, and the X and Y variables.
Sorry.
Yeah. Of course.
More questions?
Have you tried something for the non-keyboard?
It's a bit more complicated. You definitely can't do the coastal complex stuff just like that. So
Could you
not as
repeat
of
the
now.
question for what?
Yeah, the question was, have we done this for with K4, graphs with K4? And the answer is no. We might think about that later, but we haven't done anything in that direction yet.
Good. More questions for the speakers?
Yes.
Do you have any sense of how close the linear boundary is?
Do you mind repeating the question for that?
The question was if we have any sense for how close the linear bound gets. Can you expand that?
Like, if can you go to the slide with
What do you mean? The
like, yeah.
wait.
Or maybe linear strand.
Yeah.
Oh, okay, I misunderstood. Never mind, sorry.
Okay. Yes.
Great. More questions? Go ahead.
I guess it seems like you've shown that the Betty numbers only depend on the number of edges and triangles in your graph, right?
For a
For
specific case, yeah.
Oh.
Very restricted case.
okay. And you've shown that the Betty numbers are the same for an initial graph and
Ideal.
an initial ideal, an initial ideal and like the binomial edge ideal. Is there any reason like there's so much fluidity between like Betty numbers being constant and you having like all these operations on both your ideal and your graph that kind of like change its shape?
Well, I mean, okay, like in this instance, sorry, like this proof utilizes basically leading binomials. If those are the same for the 2 ideals, then you get equivalence for free, basically.
Okay.
But again, like if you add in the K4 and you can't use the Kazoo complex, like I'm sure that changes.
Okay.
It's kind of just a result of how nice K4 free closed graphs.
So like the freedom in the graph, like only needing to look at like triangles and edges comes from the like algebra of.
I mean, I think the niceness, like only having to look at triangles and edges is very reliant on your only maximal clicks being triangles.
Okay.
Because if your causal relations, equivalent relations are coming like both from the same kind of click,
Yeah.
then you get a lot more niceness. But again, like you add in the K4 and the result is.
I guess there are 2 reasons why it's nicer when there's no K4. One is like the isom, like we don't have to do the quotient thing with that isomorphism. And two, what Zoe was saying, the leading the leading monomials for all these Egon-Northcott relations are actually, they're all co-prime, which is not something that happens when you have K4. And
Like you don't have to deal with this. If you don't have a K4. Yeah, which is exactly what this is saying.
So have you looked at any graphs that have no induced K4 but aren't closed?
well, not as of yet, but it's not likely that they would have, the Riesz algebra would be generated by the Egon-Northcott relations and the Kosovo
Yeah, so I
relations.
think like this theorem, it only applies for closed graphs.
Yeah.
And it's very nice to be able to just kind of know what things are gonna look like.
Very nice.
So if I somehow magically had a graph, maybe that didn't have any, like, maybe not necessarily closed, but also didn't have any two-tier relations, all of this should go through, right?
Well, this, well, the part where the isomorphism thing is fine, but there's several things that would go wrong. One, the initial ideal is no longer generated by things in degree 2. Two, we still don't know that the Egon-Northcott relations and the Kosovo relations are the only relations.
Yeah.
Maybe there's some class of graphs for which this is true. I don't know.
All right, we will continue to ask questions later, so let's thank our speakers.